Question 3. On this question, we test the quantitative test scores, predicts the statistics test scores. Um, there is only one. There's only one single predictors. So one predictors means like we need to apply a simple linear regression because we have only one predictors and one outcomes. And then once we fit the simple linear regression model using these two variables, we need to look at whether the model fit well to data first. So it's more like dichotomous decision to see whether the model significantly explain the variance or not. So this is really similar ideas. This is exactly the same ideas as ANOVA. This is why we report F statistics, same as in the ANOVA. And then the second question, how well the model predict the statistics scores. So once we find out that our model significantly explain the variance in the outcomes, then we are interested in the strength, the amount of or the degrees of how our model predict the test statistics test scores. So this is the matter of degree. And then once we check these two, then we want to interpret the meaning of the coefficients. In these questions, we would like to look at unstandardized coefficient first before talking about the standardized coefficient. Let's move to the data. So go to analyze, go to regression, go to linear regressions. So what is our dependent variable? Dependent variable is statistic test scores. What is our independent variable? There is only one single independent variable, quantitative test scores. Let's move to that independent variable. And then go to statistics. What we need is estimates of regression coefficients. That's the parameters that we want to look at. So, and then in addition to that, we also need to look at the model fit, whether the model fit well to our data. So we need to look at the estimates and model fit, and these two are the default setting of SPSS. So just keep it there and continue and click OK. Then you will get 4 tables. Among them, these three are the most important tables that we need to look at. So I'm going to copy that. Let's paste it here. Let's talk from here. So first, let's look at the first question. Is the model significantly explain the variance or not? It's more like a NOVA question, right? So there is a NOVA table. So this is for the variance. The model significantly explain the variance or not. So there's a statistic and significance values for that associated with the F statistics, and then degrees of freedom. I know you all just know all about this, so I'm not gonna explain that more. Just so the model significantly, actually this is less than 0.05, so the model significantly explain the variance in what? Our dependent variable. And then you report the F and P values for those tests. And then how well the model predict the statistic test scores. It's about the kind of effect size or degrees of how your model fit fit to data, right? So we learned the effect sizes, and then the common effect sizes in regression analysis is R squared. And we talk about that R squared is actually a little bit biased because if we have more parameters, and then usually R squared would goes up. That means R squared is not quite like fair measure of effect sizes. So what we need to look at is actually adjusted R squared. So adjusted R square gives some penalties to the number of parameters. No, sorry, number of predictors, or so-called like complexity of the model. So it is a little bit more fair measures. Let's look at model summary. This model summaries would give us the measures of effect sizes, such as adjusted R squared, and you can see the R squared. But what we need to report is adjusted R squared. Usually, adjusted R squared is slightly less than R squared. So you can see that, right? It's 1.17. It's a 0.15. So the model explain point one po- 0.101, and then if we multiply this with 100, it would gives us the percentage. So the model explains 15.1% of the variance in statistics test scores, and then you report adjusted R squares over here. And then the last one is about the regression coefficients. So it would show the strength of the associations between the predictors and outcomes. And then two things. Let's look at. So how strong the association is, that means we need to look at the coefficients. So there is a multiple columns. The first one is about the model, and then the by model I meant the predictors. So we have quantitative test scores as a single predictors. What is the constant? This constant is intercept. So for instance, it's a linear relationship, so we could draw this kind of linear lines, these kind of lines and the x and y coordinate. And then the linear relationships usually function of x, and something else to intercept. So simply y equal intercept plus coefficient and x, right? So we plug in some values of x, and then the coefficient would play some role here, but always the baseline is the intercept. So that means our intercept is we all the values are begin or start from here. This is the baseline. So but usually we rarely look at the intercept in regression analysis, so I'm not gonna talk about this in depth. So here, another columns are unstandardized coefficient and standardized coefficient. So we actually usually report the beta, but for the question 3, we will report unstandardized coefficient. And then the associated standard error and the t statistics and then significance level of these values. So what does that mean? The null hypothesis of these t statistics is the coefficient, our beta is equal to 0. That means, hey, the slope or the effect of quantitative test scores is 0. That is our null hypothesis. But we will reject it because it's less than 0.05. We're gonna reject this null hypothesis because P is like less than 0.05. What does this mean? B is not same as B is not equal to 0. This is why we kind of accept this value 0.633.